So welcome to West of England Combined Authority offices. Quite possibly a first for many of you, but it's a significant organisation for the region, and there's some people from the Inward Investment team and Combined Authority. You can answer any questions about the Combined Authority later on. So thanks for coming, thanks for giving up your time, and thanks in advance for participating in this. This isn't going to be a didactic one-way conversation. I'm expecting input, and I will be trying to force input from all of you, because this is about trying to solve a problem and create an opportunity and find solutions to that opportunity. So it's for all of you to participate in. So we're all familiar with the pace of change. We often talk about the pace of change of technology, and that pace just is, unfettered at the moment. And the computing power that we use to feed us the information that we use, the data, the analysis of data that we feel the need to consume. Greg's already on his phone. The processing power there is so massively different from what it was, and that's great because we can do so many different things. We can solve problems better, but that comes at a cost. We've been through this kind of process of, well, we don't need to fly to have that meeting. We can have a Teams call, or we can have a few Teams calls. But what is the carbon footprint of that Teams call, especially if you blur your background and the processing power there? These calculations start to be more complicated. So it's a difficult problem, but what we do know is that our hunger for data and processing and compute and analysis of data is going like this, so is power consumption. So the opportunity we've got is to change the rules, if you like, and find better ways of doing this. There's a technical piece to that, and we're going to deep dive into a bit of technical. It's not going to be too technical, and for those who aren't technical, just hold your nose while we go down deep for a bit. But it's useful to set the context, but it's also about how we build, how we organise, how we set policy, and
good.
And all the pieces that make this, how do we solve these problems? And the particular interest point for us today is how do we make West of England the place where we really push the boundaries and help to solve these problems. This place that we've got colleagues from the Dept Business Trade and Science, Innovation, Technology with us, and we've just come from a lunch where we've been looking at all the facets, the strengths of the region, and the diversity of the skill set. But also what came up within that was a subversiveness, a comment about how this region is a little bit subversive, a lot pioneering. We push the boundaries. So we've got an attitude to solve some of these wicked problems, but we've also got the technical capability. So that's the question that we're going to be asking. What do we need to do to make this place the place where we really solve these global challenges? So, as I said, it's a collaborative process. I'll engage all of you in that. And to start with, so we're going to listen to Alan giving us some context and a bit of technical deep dive, and then we've got a varied panel to help facilitate that conversation. So, Alan, off you go.
Okay. Well, thanks, Nick, and good afternoon to you all. Thank you for coming along. So I'm going to be presenting from the position that we need to redefine computing architecture from the ground up, with energy efficiency at the heart of every decision we make. And I believe that the West of England has an opportunity to be instrumental in the planning and building of a community where energy-centric computing is ubiquitous. And hopefully this presentation will give you this detail. If I can get anything to go forward. There we go, technical problems.
It's a Mac, isn't it?
Sorry. Apologies, guys.
Why would be low energy? I think it would work.
Yeah.
Okay.
There we go. All right. So, as Nick actually just mentioned, the energy consumption of computing today actually consumes about 3% of the world's energy. And it's on a trajectory, as you can see from this graph, to take up ever more percentage of the world's energy. And that's because we need more and more compute, and so we really need to double down on ways of innovating in the way we do compute to keep that energy at bay. The way the industry is currently dealing with this, we have massive amounts of compute performance for the way these AI applications are being tackled today, and the energy efficiency is a critical factor. So we've got proprietary compute architectures are being built by all of the incumbents and some of the startups, as you'll see in more detail in a moment. And the problem with these proprietary architectures is they're not accessible to the rest of us, and that means innovation is limited. If we take, so really the architectures we've got today are just the old open architectures, that being basically the IBM PC from 1981 is still pretty much used today in the servers that we build. And to take a startup close to home here, GraphCore, you can see their chip, and they would simply build a PCI card like they have, and that would be inserted into a traditional computing architecture we know today. But even GraphCore, that wasn't going to be good enough, so they had to create their own proprietary. They created their own chassis with multiple of their devices and other devices in. They created their own 19-inch rack with their own machines in, and they created their own data center. And on top of that, they had to write an entire software stack to even begin to compete with the likes of NVIDIA. And that took $710 million of venture capital money. So really, this approach is untenable and arguably anti-competitive, and that's what we need to really address. Looking at the energy from the core thing that we're all talking about today, ChatGPT and the likes, if we look at the human brain, I've just given you a little set of parameters there of looking at the human brain from a type of compute. I'm not going to bore you with the details of this, but if you'd like to read it, you can. But if we compare that to a classical compute, so we've normalized to one human brain, we need around 100 petaflops of compute performance to be equivalent to one human brain. Now that's a widely debated figure, but just take that as a rough rule of thumb. And when you look at today's supercomputer called Frontier, about 10% of that is 100 petaflops, and that needs 2 megawatts of power to do the same compute in what our brain does in 20 watts. That is many orders of magnitude of compute that you need. So we do have a tremendous opportunity to innovate and actually get closer to what our brains actually do. But that said, we should look at the way the brain actually works. There are several features that we're trying to emulate with AI compute today. But it's worth noting that if I asked any of you to multiply 2 numbers together, you'd at least take a few seconds, some of you maybe longer. And whereas a computer will do that in a single clock cycle, which is a fraction of a nanosecond. And so there are tasks that a classic CPU is far better than the human brain is at. And so what we're seeing happen today, it did happen a long time ago, is a proliferation of these processors and accelerator technologies, and we call that heterogeneous computing, which I'll touch on in a little bit more. We've got a long way to go, and there's a lot of opportunity basically. Now, from a West of England perspective, it's really steeped with computing expertise, going back a very long way. And just to give you my personal anecdotal experience, it's a fairly interesting backdrop, which I think just epitomizes what we have here in the West of England, is I started as an apprentice with British Aerospace in Filton, and we built what we would call today augmented reality simulators. And so this is a little example of that. On our panel is Professor David May, the inventor of the transmuter back in the 80s. and starter of a company called Inmos, I'm sure many of you are aware of. We actually used many of the transputers in this particular simulator at the time. We also pioneered the use of FPGAs, field programmable gate arrays. They are an accelerator in use for compute acceleration. And we achieved 100 times faster for certain algorithms than Intel's fastest processor at the time, called the Intel i860. And also, when you compared the machine we built with the #1 supercomputer in the world at the time, the Silicon Graphics Onyx 2, that I'm sure most of you are familiar with Toy Story. It was a fantastic feat, the animation of Toy Story at the time. That machine was used to build that. Our computer for this simulator was 100 times lower latency in terms of the video path delays. And so that's just an example of what this region is actually capable of doing. And it proliferates across the entire area. Now, by the way, that technology is now coming back full circle. That was a heterogeneous computer. We went very homogeneous, just Intel processors, and now we're coming back to a heterogeneous world today. So what's driving computing architecture? Well, first we've got sustainability. We need ever-increasing compute performance, and that has always demanded that the energy efficiency is always being addressed. But now we really need to double down on the energy efficiency part of it. But as well as that, we've got an opportunity for energy recovery and energy reuse. A computer today, 90% of the energy it consumes is exhausted as heat. And that gives us an opportunity for recovery and reuse of that heat, as we'll touch on in more detail in a moment. Looking more broadly in the emission reduction, and we're trying to achieve net zero, it's actually defined as three different scopes. Scope 2 is what we all pretty much understand. It's certainly in my industry, it's the power consumption of the computer itself. But Scope 1 covers the on-site emissions of the actual facility that the machine sits in. And the biggest one is causing a lot more focus these days is Scope 3, which is called embodied carbon emissions. So that's the actual energy that's consumed to build the computers that you put in the data center. So if you're refreshing your computers every 3 to 5 years, like many data centers do, you're actually, the embodied carbon is thrown away and started and used again. So therefore, that's another one that the industry is heavily focusing down on. So we've got to cover all of these. Then this one's an interesting one. We've got this, what we call this domain-specific architecture composability. Now we've got all of these heterogeneous accelerators that can be mixed and matched to make an application run really fast and really efficiently. We need to be able to compose these fairly quickly when we build a machine. So I'm showing 4 different versions. We've got a fixed architecture that's really not composable at all, but that's really great. The Apple iPhone is a fantastic example. The silicon chip has been so optimized for performance and energy efficiency, but it's fixed for that one operation. But hey, there's billions of phones out there, so that makes sense. At the other end of the scale, our classic server architecture is a very pluggable machine. Every piece of the server is pluggable, from the processors to the memory to the accelerators, the power supplies. Everything's pluggable, so it's very composable today to a particular application. But there's 2 other areas that have been emerging in our industry today. I've called this one hard physical composability. We're effectively compressing the entire compute server down into a single package of a chip. And as you can see by that diagram, these are what we call chiplets. And so they have the different processors or memory that we put together inside the package. It's quite expensive to put it together inside the package, and it's not very configurable after that, so it's called a hard physical composability. And at the opposite end of the scale, we've got what we call dynamic software composability, where we take all of the compute resources of memory, storage, processors, accelerators, and we put them in separate drawers in a 19-inch rack, and then we recompose, the software composes them depending on the application's needs. So at one end, we have these hardware experts that are really focusing on energy efficient, what we call hyperconverged chiplets. And that's because most of the power in compute is in what we call the data movement. That's where all of the energy is burnt, really. The actual compute itself is a relatively small amount of power compared to moving the data around. And so this is a great achievement in terms of reducing the energy by combining it. But sadly, and oddly enough, the software approach is very energy inefficient because we separated all the pieces apart, and therefore we're moving the data even further, and so therefore we're consuming more energy. So on the face of it, disaggregation doesn't make a lot of sense, but the software world wants that. What we need to do is we need to get the hardware people talking more with the software people, and we need to try and bring these two together of how can we do both. And finally, the piece that's driving computing architecture is we've really got to drive the costs down. You may not be aware, but these proprietary architectures from the likes of NVIDIA today are like $500,000 for a box that goes into a rack. So we really need to start to drive these, and the only way to do that is with open architectures. And so this is where I come in. I'm part of the Open Compute project. So that's Facebook started that over a decade ago, along with a smaller company called Rackspace. And the idea was, for their social media platforms, the traditional compute servers were not solving the problem. They needed it. Their focus was social media, so they were building their own hardware, but they were trying to give it away to shift the industry forward into a new world of open computing. And I'm the actual technical lead for one of the groups called the OCP High Performance Compute Sub-Project, and that's what I lead there. And I'll get into a bit more detail there of what we're trying to do with an energy-centric computing focus. So over the years, I've specialized in compute architecture, and I've came with this very abstract view of what the computing architecture should look like tomorrow. And we have the pieces in place to a certain extent, like from the cloud to the edge to the intelligent Internet of Things. We want to look at that all as one large computer. So when we think of the cloud, we think of the big data centers. Maybe they play a part, maybe they don't in some of these systems. But then we have what we call the edge compute. So this is where, this can take many forms, like a base station in a telecom tower, or one of these telecom units on the side of the roads, to offices and homes, and also to schools, etc. And the compute in them, the edge compute in them, may take different forms in terms of the physical size of the compute required. And finally, we have the edge side of things as well, which can take many different forms. I've got a few examples here, like an EEV or an augmented reality headset or a drone, etc. And so that makes up the computer. So you see, this is what I'd like you to take away from this is we should look at this as one computer, where when we write the software for it, we go for the exercise of where is the most energy efficient implementation of moving the bits of software into the different pieces of the cloud, the edge, and the IoT. So just going back to our diagram again, if we look at the cloud and the edge, we can actually turn this into a fairly simplistic Lego building block of the compute, which can take a number of forms, and the memory that is attached to it locally, and that memory being shared, the data being shared across multiple units. So we can step and repeat a fairly simplistic building block across the architectures is the idea. And this is what we're trying to create in reality. So I'll now show you a little animated model. So this is the high performance compute module. That's the media, that's the memory just being unplugged there. And then there's heat sinks around it or carry the water to cool this module. This module can be burning in excess of 1 kilowatt of power, potentially, depending on the processors going on it. So it's like one of your bar fires at home. It has, the I/O is connected between modules with cables. And then this is showing the big processor in the middle that will run the various pieces of your application. But this module can take many forms of heterogeneous processor, and I've labeled a few here: CPUs, GPUs, FPGAs, even optical modules. There's a bit of optical computing coming in now. And the question mark is, this can also be your module, or if you're a new startup like Graphcore and you have a great piece of innovation, instead of having to build the entire data center, hopefully you just need to build a module and you can become part of this big open ecosystem. Putting this module back together, we reassemble the water cooling jacket, as you will see a bit more in a moment. We reassemble the memories. That's a water inlet. We basically plug this into what we call a wall of compute, and this is a single piece of the wall with the water and power. You might be familiar with water and power being in your walls at home, so it's not too dissimilar to that. And you mate this individual module into its wall where it gets its power and its water. So here we're showing a wall of just the wall piece, unpopulated, and then we can populate the modules with simple blind mate, plugging these modules in, and again they can be all different flavors of modules that go in, but they're in the same common format. So if we look at what we've done here, and why is this, what are the sustainability features of this? Well, if we look at those scopes, from a scope 1, reduce operational emissions, we've got the cold water coming in and the hot water coming directly out of these modules, and that's controlled so that the temperature out is 65 degrees C, and so therefore its energy is recoverable. And for instance, we have the Bristol heat network here, so potentially this could be fed into the Bristol heat network. From a scope 2 perspective, lowering the power consumption of the computer itself, this architecture really allows you to build any domain-specific architecture. So that has some tremendous benefits of saving energy when you build a machine exactly as your application needs it. But because this is a miniaturization and the modules are all much closer together than a classic 19-inch rack, we've got less data movement, and we have a far more efficient power delivery mechanism here as well. And finally, from the scope-free indirect emissions, the modules are using far less raw materials in the first place, and they're all built and used from a common reusable building block. And so if you wanted to upgrade a module, you would maybe get rid of the silicon if you had a new piece to go in, but you could reuse all of the mechanical pieces around it because everyone uses exactly the same step and repeat format. And therefore the embodied carbon has much longer life to it as well. So we're both reducing the raw materials and we're using them for longer periods. So in summary, we have an ever-increasing percentage of the world's energy is really required for computing. And we've got proprietary solutions coming onto the market that are really stifling broader adoption. They're a closed market to those individual incumbents. With the Open Compute project, we have this HPCM architecture where we're trying to democratize computing, but looking at it purely from a sustainable energy-centric computing focus. And this modular architecture can really provide a low barrier to entry for new innovations from new startups. And I believe the West of England's heritage and expertise can be instrumental in this shift, with its aerospace and defence roots, which really burgeoned a lot of this, and the long history of academic and research in computing here, as well as the forward-thinking, progressive infrastructure and planning mindset, as we are all here to discuss. And with that, that's me. Thank you very much, and take us into the panel.
Thanks, Alan. So while our panel take their seats, any questions for Alan that arise? Do you want to introduce yourself while you go?
Will Cormac from Softcat, a chief technologist there. Quick question for me. In relation to sort of your proprietary chip providers with this NVIDIA, Intel, I guess AMD, what's this kind of this architecture? See, are they thinking of anything similar to this? Or is this something only we're looking at?
So if you follow the tech industry, NVIDIA actually moved to it. In fact, I do, just so you can pass this around. But this is the module itself.
Very Blue Peter.
Blue Peter. And
there's no sticky back.
and here is the actual, the PCB part, the computer part of that, right? So NVIDIA really moved from the standard PC card to what they call a module like this. So if you look at their DGX boxes, you'll see the SXM module. They made it. I was involved heavily around when this happened, and I tried to use this, and then they made it proprietary. Jensen said, nope, nobody's having it. Then the OCP said, well, if you're not doing it, we'll make something called the OAM module, the OCP accelerator module. And that was so that everybody else, including AMD, could make a similar module to this, and that would go into the other computers, right? So everybody else is doing OAM modules. Today's frontier machine, the number one supercomputer in the world, is based on OAM from OCP. So the industry standards are going there. But the only thing is the architecture. When I was working heavily in that module, I was involved in all of that, and I realized that it wasn't giving us enough domain-specific freedom and the energy required. Without getting into too many details, we would use something called retimers like confetti, and they just burnt more power because it was a mess. And that was where this has been sort of in the oven for like a decade or more for me since I've been doing this, and that's really where it's come from. So yes, things are happening, but we need to push it a lot more fast, a lot more quickly.
I think the truth is that no one's really taken a look at the underlying standards we're using in over a generation. It was those people 2 generations ago who were working largely at IBM around AT that last really thought about this from the ground up. And that's kind of scary given how far we've come in that time. We've got a number of mega trends occurring in the industry as a whole. Composability is going to come along with CXL. We've seen a shift to a lot of AI workloads which will likely move towards neuromorphic, less von Neumann model processing. And ultimately the power density is going through the roof. You can see this with all the packaging. Intel are making modules. This is just standard paths of 350 watts. And the GPU folk are thinking 350 watts is nothing. That's a huge amount of power in really small packages. We're talking, a third of a square foot that's got hundreds of watts in it. And yet, none of the stuff that we've been using for nearly 50 years now ever thought that was possible.
I knew we'd start getting into the conversation. Let's take the opportunity to introduce yourselves. So, for panelists from different perspectives, I'm going to ask each panelist to introduce themselves and give their thoughts on what the opportunity is here in a West of England context. So, Freya.
Nick, thank you. Unfortunately, I have to wear glasses to read my notes, but I can't then see you, so forgive me flip-flopping between the two. So it's really interesting that Alan mentioned that he...
You are who, first of all?
Freya Lockwood. So I work in the Combined Authority. I'm part of the strategy team and part of our strategic innovation team. And my focus is on place-based transformation. So I'm shamelessly plugging our soon-to-be-published digital plan for the region, but I'm not going to go into the details. You can read that. But we're very much focused on how we enhance the digital strengths of the region to tackle things primarily focused on digital exclusion, but also around the sort of plethora of ways that we can focus digital to deliver better outcomes for people and place. And like Alan, I started my professional career up in Fulham with British Aerospace, now BAE Systems. And then about the question in terms of, what's the opportunity to really put the West of England on the map in terms of more sustainable computing? I mean, that is one of the key priorities for the region. You know, we have really challenging sustainability, climate, nature recovery targets. So we need to be focused on more things like this. What are the different ways that we can start to chip away at that? So it's a real opportunity. The tech sector in the west of England, as you've probably heard throughout the day if you've been at other sessions, is we're a tech for good cluster. We're known for being very purpose-led, very innovative, and transforming the way that we create and use digital technology to tackle some of our biggest challenges. So for me, you know, making the west of England the centre for this conversation would be fantastic. It would really play to our sort of sectorial strengths. And as a combined authority, I think our role is how do we create the conditions for those conversations to happen and for that innovation to sort of really get going and, as you were saying, pick up the pace. From a personal perspective and just, you know, some of the things that I'm trying to weave into these conversations is I feel strongly, and this is paraphrase somebody else's phrase, technology is not destiny. It's ours to shape. And so I think, as Alan is highlighting, there's a real need for a different design philosophy. And so my provocation is, what if we were designing technology in all its different forms and all the different ways that we use it, including things like this, to help people and places thrive, rather than what I observe is a focus on cost optimization, you know, stripping out sort of making things more efficient. It leads you to a very different set of outcomes. So that's my provocation.
Thank you, Freya. David.
Okay, I'm David May, and I've already been introduced to some extent. I came to Bristol to join this company in Boston, ended up designing the transputer, which incidentally was designed very much along with its programming tools. So I designed the programming language that went with it, and we thought a lot about the applications of it. I subsequently, as the company ran into various problems, largely because of the change of government that originally financed it,
Politics,
became,
mate.
Sorry?
Politics.
It became part of ST Microelectronics, which was quite a successful venture. Interestingly enough, it would never have been formed without the European Union and the UK being part of it, which is another message, I guess. Eventually I realised that I didn't really want to work in a 20,000, 30,000 man company. I was more interested in doing different things, and happened to have the opportunity to move into the university running its computer science department in about 1995. And I had a lot of fun doing that, including introducing a lot of entrepreneurial work to encourage the students to think about starting businesses and things. An unexpected consequence of that is that one of my students did something really cool, and we started another company called XMOS in the early part of this century, and it's still around in Bristol and employs quite a few people.
And GraphCore kind of came out of that.
Spun out of that, yes. There has been a fairly, I mean, it helped that I was encouraging the students to do this, because then a lot of them have actually gone out into the region, into either the hard tech companies or software development and games and so on, that the region is well known for, in fact. And I hope that will continue. I think it's very important to involve the universities and the students in this kind of activity. It will need startups to break into some of these and open up some of these new ideas, I think. I'm now sort of retired. They call me an emeritus professor, but I don't seem to be able to give up really, so still talking to the students in particular. Right, now a few notes here, which I was sort of partly confused about whether we were talking about energy efficiency or sustainability. I know they're related, but there are one or two dimensions to sustainability as well as the energy efficiency. One thing I have discovered, to my alarm, when I started looking closely at high-performance computing and what was going on, partly because I was involved in setting up a lot of Bristol University's high-performance computing, and you've probably noticed that we've now got drawn into the UK's largest AI computer here, which is largely on the back of what we've been doing for the last 20 years. when I started looking closely at what was happening in this area, I was rather surprised to find that these machines that are being used in the cloud are largely, as you said, based on very old technology. I think a curious feature was that around about 1990, there was a huge amount of work, and we were involved in it, working out how to build very general purpose parallel computers. In other words, sort of simple building blocks combined in straightforward ways to build much bit more complex systems.
By the application was the DOE particularly were funding this.
You could do this and so on. And somehow or other, I think what happened was that there was in the 1990s, there was a massive growth in the market for PCs and stuff, and then subsequently for smartphones. And that's what actually provided the investment necessary to build these faster and faster conventional processors. And if you look at the costs involved in building the manufacturing plants and so on that are being used to build these chips, it's astronomical. I mean, these smartphone chips that Apple makes use of, made in one of two places, Taiwan Semiconductor or Samsung. These are the only places in the world where there are factories that can actually build them. They're both incidentally dependent on a single supplier of the manufacturing equipment that's based in Holland. Yep. So the supply chain is very fragile indeed for these things, which is a source of concern to me.
You literally run a space program with the amount of money it's costing.
Yes, and I don't think making copies of those manufacturing plants around the world is a good idea either, because that's a quick way to destroy the planet. So from a sustainability point of view, I don't think we should allow ourselves to become dependent on these very fragile supply chains. Now the other thing is that actually, when I started digging into the details of them, they have become incredibly complicated. The architectures inside the processors and the way the processors are put together are very difficult to understand. I speak as somebody who's been doing computer architecture and teaching it for the last 30 or 40 years. So I know, and even I can't understand parts of the 1,000-page manuals that seek to explain it all. So the consequences of this is that actually it's very difficult for a programmer to actually optimize applications to run on these machines. And I have examples of programs that run 30 or 40 times differently in performance, depending on details that will be completely invisible to a typical program.
To be honest, the F-35 program, I think, really serves your point.
So these, and we can see that in some cases where people have been prepared to put the effort in to really optimize some things, you get a staggering difference in performance. And what that tells you is that a lot of that stuff that's being installed at great expense to the planet and in dollars, and then run with energy and so on, is actually wasting energy. It's doing nothing useful at all that couldn't be done with a better design to start with. So this is an issue, and the other issue that goes along with things becoming too complicated is that when you get to my age, you do worry about how you pass know-how on to following generations. You can't make sense of it. And so how is the next generation going to actually understand how to build the things, build the manufacturing plants, maintain them, and so on? It's a big concern, this one. You won't find any suitable textbooks that explain it. And you won't find very many people in the universities that know how to explain it either. Okay. So there's a sort of sustainability thing. I suppose I should say something about what I think we might be able to do about it. Yeah. I absolutely agree with the principle that we should be improving the quality of life for everyone. And I don't like these sort of people who talk about we've got to do economic growth. Economic growth over the last 10 and 20 years has basically had the effect of transferring more wealth to people who already have it, as far as I can see. So forget growth. What I want to see is programs that will actually, where the main aim of them is to get everybody a good standard of living and good quality of life. I would also like to see us pay attention in the way we approach engineering to, well, two things actually. One of them is engineers should be challenged to look for the simplest solution to things, not the most complicated one. If I want to control a light bulb, I want a switch, not an Alexa and a cloud.
That's my favourite example as well, funny enough.
And I'm intrigued about the situation we've got into to do with these complicated supply chains and the fact they've become so localized into places like Taiwan, which are prepared to throw an enormous amount of investment at some of these things. I'm still trying to find the right person to ask this question, given that I think you could actually get away with a much simpler manufacturing process than is currently being used. The question is then, could we actually design a manufacturing process for this electronics that could be installed anywhere?
Yeah.
You know, it's as I say, it's because of this adoption of the designers of these chips have largely been driven by the motivation to have the peak performance figures, to quote.
Yeah.
So they put in stacks of clever optimizations. If you're able to make use of all the optimizations, you'll get the peak performance.
Driven by the benchmarks.
Yes, so there are one or two very carefully selected benchmarks that we always do.
I've sat having the dinner with NVIDIA's founders where they've told me they built a business beating benchmarks. That's all they do as a business.
That's right. And if you look at the HPC benchmark, is low pack.
Yeah.
The machine runs at full speed
Yeah.
once everything's been carefully optimized. If you go and throw a different application in, it's performance awful.
Yeah.
Usually. Okay. So there's an interesting one. Could you have basically a complete sustainable supply chain here or somewhere else, or in Africa or India or wherever you want? I think we should be able to build our computers everywhere from the manufacturing through to the computing infrastructure that we need in a way that's much more distributed. After all, we're distributing energy supply these days. We're putting windmills and solar panels and stuff. And there's no reason why I shouldn't be able to stick a server in my home that will deal with the voice queries that I'm putting to switch the lights on and off. So I like the idea of a rather different environment here. I find the phrase globally connected, locally self-sufficient is I think the
So
aim.
what role does this part of the world, Bristol and Bath,
Well,
play in
I
that?
think
Briefly?
I think it's a good community. It's got the hardware, software, and applications. A lot of the relevant expertise there. I think we should be careful to involve the educational community and all the way through. I think the kids need to understand a lot more about technology than they do at the moment, and they should be involved.
Not just as users.
Not just as users. Absolutely not just as users.
Okay.
I think we have a good culture as far as startups are concerned, with involvement in universities and beyond, as you know, and I think that's I guess what I put down here.
Brilliant. We'll come back to you, I'm sure. Thanks, David. Rob.
Oh, and by the way, the transmuter idea is still relevant.
Rob.
Our boss still uses it.
Good afternoon, everyone. Rob Williams. I'm probably the odd one out in the whole crowd. I operate definitely in the brain and the post-it note because I'm a builder, basically. And I started in construction 37 years ago. And 37 years ago, sustainability and the only thing we discussed about carbon was you'd have a spill kit on site that caught the diesel that the guy was filling up the machine and spill on the floor. And that was about what we talked about. And I'm here really to share with you that construction has just gone meteoric in the last 5 years by way of carbon reduction. So pretty much every single meeting, every single building, everything we do nowadays in construction is around reducing carbon. So you may not know, but we build, my company are national, I run the Southwest, I've built
And the company is Morgan Sindall.
Morgan Sindall, yeah. So we're a tier 1 contractor, we work in Bristol, we work in a lot of South Wales, Southwest, I've got jobs all over the Southwest. We build an awful lot of schools, so in the last 6-7 years, I've probably built about 35, 37 schools. Loads of primary schools, loads of secondary schools. And in the last 5 years, the drive has been net zero in operation. So I'm proud to say every single school that I build today and every single school that I finished in the last year is net zero in operation. We're not quite there with embodied, but embodied targets are flying down at a faster rate than construction can keep up with. So I was talking to Alan, and one of the challenges with a school and net zero is, yes, you cover it in PVs, yes, you create enough energy that it uses. But I did a bit of a calculation earlier on, and schools are shut 169 days in average of the year. So they're only about 54% use of the energy they create. So one of the big problems I have with all of the jobs I've got, every single one of them's got a problem with this. The infrastructure, obviously you can pay the electricity back into the grid if they'll buy it. And the infrastructure is not there in a load of places to use the energy that we're creating on the days that we're not using it. So then we look at batteries, and the problem with batteries, the schools don't use them for 6 weeks in school holiday or 2 weeks on half terms. So we're not using the energy. So I got talking to Alan, and he said, well, I know a way we might be able to use the energy, and there's ideas around what we can do with that. The other thing we've built recently, and we finished it about 18 months ago, no, probably 2 years ago now, is we built an energy positive building. So to look at it in another way, with Newport Talbot, we built a building which was primarily spec labs and office spaces, and it creates more electricity than it uses because the vertical walls are PVs. If you're 100 yards away, you would not tell. You just think it's cladding like any other building. But that building in the last years created 70 megawatts of electricity more than it's used.
And I think what some people don't realise is our data centre buildings are some of the most complex and energy intensive buildings you'll ever find. I mean, I used to spend a lot of my life in Tully House in London, Coriander Avenue. And that place is the nerve centre of the United Kingdom. That's where all of your internet transit goes in and out in some way, shape or form. And the amount of energy density is still phenomenal. Yeah, it's 100 kilowatts of rack type of numbers now. And so we need to get more of you guys in the construction bit involved in that because we've got.
So we're into buildings, and we cool the comms rooms, and we throw energy at cooling it, and we throw the energy out the window, we throw energy out the room. So people don't realise every single building I'm building at the moment has got air source heat pumps. We're not putting gas in schools. It's ironic. You can actually, I don't know if you know this, you can buy an electric Bunsen burner because they still like doing silence. They're not very good at the moment, but there's ways around that. So the only reason we put gas into secondary schools is because they like Bunsen burners. And
it's like mathematicians and their chalkboards.
Yeah, exactly.
Yeah.
And we're changing. But there's loads of things we're doing. We're driving embodied carbon down. There used to be a thing, you've all heard it, reduce, reuse and recycle. That's just old hat now. We should be looking at stopping, restoring and replenishing. Don't think about how we could do things slightly differently. Think about how we can do things.
And the opportunity at city scale, city region scale?
Yeah, so the opportunity is there's lots of buildings being built. There's lots of buildings being built, so why not piggyback on the back of some of these buildings? Now, there are challenges. If you're going to get net zero carbon operated building, it needs to be oriented correctly, you need to super insulate it, you need parameters. I do a lot of talks with educationists around, you may not like the environment all of the time, because people are humans and they love to turn the AC on and they love to, turn up the heating. If you could just allow it to take a little bit more time, because super insulated buildings take a little bit more time to heat up and cool down, and we're not used to that. We like the plumbing. Interestingly, final point. Primary schools don't get air conditioning, because when it's too hot in a primary school, they check the kids outside and they say, take your jumper off. And I find that really interesting. So we have to cool secondary schools because they like the kids in front of their computers all day. Even when it's 32 degrees outside, they want it 23 inside. So I think it's a challenging mindset as well.
Okay. And last but not least, great. And then we will get some conversation with everybody else in the room.
My name is Craig Compton. I'm kind of the power user here in many respects. My background is a signals processing engineer by training, but about 14 years ago I read the original work of Jeff Hinton on deep learning, and having been in a telco where people kept coming to me with these business problems, I've got good customers over here and bad customers over here, find me more good customers. And I was like, well, unless someone can come up with a heuristic curve for me for that, there's no chance of that happening. And I was like, we must be able to build these machines smarter. So I set about building on Jeff's work, and we run a AI skunk works, predominantly for national security applications, but we work in automotive, aerospace, various other things, where we are putting real intelligence in the kind of human cognitive sense into devices, and trying to solve that fundamental issue of how do we get human type fuzzy logic behaviour into our systems so that they, if nothing else, interact and benefit us more, rather than us having to work the way the machines want to. They work in the way that suits us. So a lot of my time is in works with high performance computing, because we have to train these systems, which tends to be a hugely energy intensive task and requires a vast amount of processing power to do. We're very much neuromorphic aligned, so we try and replicate how the human brain works, because at the end of the day, us humans are the reference model. Anyone who tells you otherwise, by the way, is having a laugh. Unless we can build a system that's better than us, we shouldn't try and get too far off the reference model. So that's very much my background, and that's where I kind of come at all this from. How are we going to make the next generation of systems scale for what our ambition is to develop really intelligent cognitive systems?
So, it's not just about the chip. There's a whole load of things that we touched on here: buildings, policy, talent, what we do in schools, the entrepreneurship piece, actually what it is we're creating and how we're kind of shaping usage of things. How can we share resources across that piece? So I'm interested to hear any observations, reflections, provocations, disagreements from anybody in the room. So if anyone's got anything to say, please do. Just put your hand up. Mark, you're about to put your hand up. If you'd like to introduce yourself first, and then.
Chief Strategy Officer at the Centre for Modelling and Simulation. So we were open at a data centre, we were on HPC, we're power users off that thing. We also develop applications, we were adopting DM that has to use less than 5 watts of space applications. So all of this is very much pushing it open the door. But I want to pick up on the thread you raised in your introduction, which was the subversive potential here in the region to do something meaningful. So I'm interested in maybe Alan and the panel's view on what are the concrete things as first steps we could do to draw out the art of the possible in this region when we pool those resources there's managed.
Concrete steps.
Same thing I've always liked about Bristol. We've got a number of Bristolian alumni who work for us. It's the rebel attitude. Let's be honest, Bristol has always been a city that, because of its port nature, etc., it was always a bit out there. I'm very much transatlantic, and I've spent a huge amount of my career in the States working for the Americans. And it's very noticeable. One of the things that has really powered innovation there, really since the 70s, is Austin, Texas. And Dell have really pushed the topic of keep Austin weird. We see it when we go to Supercomputing, don't we? There's always a huge number of Dell badges that get handed out, keeping Austin weird. And that's their thing. They're rebels down there. And that's why they invented the laptop and why Compaq came out of there. And it's amazing how much of Silicon Valley is now moving back to Austin. And I think the UK doesn't really have that kind of centre in the way Austin is yet. However, Bristol's a damn good candidate for being that.
So what are the concrete steps?
Well,
was the question?
Supercomputer is a good start point, but it is ultimately about enabling the ecosystem, which I think David, you've got a lot of experience with.
Yes.
And I think that's
Freya.
where the combined authority and sort of, to some extent, local government is our convening power to start to bring together computer experts with construction, with all those different building blocks, to start to engage those conversations and go, okay, do we all agree this is the right way to go? And if so, how do we get there?
Because we're talking about a huge issue and trying to change things globally, and that's difficult to think about. How do you boil the ocean from here? Pun intended.
It's cruel to run, right? You've got to have a first step. And some of that is, like you say, it's convening power. It's getting all the folks in the room who own the different aspects of the problem, so we actually get some steps going.
So there's a lot of dynamics going on, obviously. I guess one of my core points in the presentation was computing is going ubiquitous, right? And to David's point, you don't want a light switch to be to go all the way up to the cloud and back down just to turn your lights on. But so we are definitely, as a community, I believe, that we are getting more and more embedded with computing. It is going to be ubiquitous. It's going to be a very interesting world we're going to live in even just a decade or two. And so the opportunity is, we've got time. We've got to plan our way into that. And if you think about, if you take as a like the combined authority here, as a region, if you look at the vision of where we are actually going, and then you wind it back to where we're at, then it's a case of, can you start to, like the planning that Rob's talking about there, so solar is in everything that guy does every day. The heating is everything's there, but the computing is sort of one of these things you buy and you stick a box in your study, right? It's like, can we start to architect the building and actually have the computing in there and the heat driving, more heat.
So integrate buildings with.
Could we get
So
that?
so the spec of the building is not just the number of rooms and the square feet. It's
Exactly.
actually the number of flops that the building has.
And you may, and it could be like solar. It could be when you're in the house and your Android is there cooking for you and whatever compute it needs. It's consuming that amount of power, but you've got more compute power for, let's say, that when your neighbours need it, it gets.
So
it's covering.
The other one that's interesting is the network part of all this stuff.
Right.
I don't claim to know anything about what the efficiency or lack of it of the internet is, but it does occur to me that an objective to produce the sustainable network might be an interesting thing to explore.
It's like local food markets, isn't
I
it?
just basically like the idea that you don't want to get the kids to do this kind of thing. You're not allowed to connect onto the internet. You're allowed to build your own network and stick your own computers in your rooms. Go play.
So can I ask the audience, anyone here, the concept of you've got a business, you grow the business, you need a new office, you commission a new building, you get Morgan Sindall to build it for you, and you specify, as well as the square feet and the energy efficiency, but also the compute power that you can plug into within that. Any kind of users? Is there Alan from Yellow Dog here? No, that's a shame.
It drives me mad when we go to buy buildings that, like, it seems to be the last thing anyone thought of. And for a company that is compute heavy, we go into buildings where there's nowhere near enough power, no one's thought about the comms, it's all an afterthought for construction. I end up basically having to rip half the building apart to get it all going. Done.
Any perspectives on that concept? The lawyers in the room? Any lawyers in the room?
You go on there.
Go on. Do you have a legal? What's your area of law? You're not the planning guy. Okay. There was a planning lawyer, infrastructure lawyer, but okay, I take that as a no.
One of the,
Go Freya.
Can I sort of lift the conversation up to sort of a sort of more strategic view? So something really tangible that we could do, and it wouldn't take much to convene the right people in the room, is kind of having a conversation about what would our vision be. So given where we want compute to go and the opportunities to join it up with other things, so what might a vision look like, and get consensus around that. And then have a think about, okay, well, what's our current trajectory? If we do nothing, where are we headed? Okay, where's the gap? And if there's a gap, how do we course correct? And having a conversation about, okay, well, what do we need to start? What do we need to stop? What do we continue? And see what comes out of that conversation.
Well, you go see already where we got to, which was London has full of multi-megawatt data centres that you require another number of megawatts to cool them. They're all clustered in one place, which is strategically really dangerous. As I say, there's a couple of data centres that are the UK on the internet.
So not very resilient.
Yeah, totally unresilient.
And I think
small power
understand
outages.
that the planning, I think they're beginning to stop giving planning
That's it.
for
Anything over 1
data
megawatt.
centres along the M4.
Yeah. Anything over 1 megawatt's gone. And partly because the power infrastructure can't cope. You start building these multi-megawatt consumers of power, that means the whole local electrical infrastructure has to be upgraded to cope with them.
So we're hitting a brick wall anyway.
We are anyway, yeah.
So talk of brick walls.
So we have a burning platform.
We have a burning platform, absolutely. Rob, you were going to say something just now.
I mean, one of the things I was thinking that's really important is, and I think in all whatever we do, there's too much waste of energy and there's too much underutilisation. And I'd be interested, you know,
Particularly
all-
low-grade heat, what Alan was talking about. The
Yeah,
65
heat,
degrees
you know,
usually should be useful. But
we can use that all day long. You know, an air source heat pump generally only creates 58, 57 degrees from outside anyway, so you know, 60 is
So getting that computing locally to where we can use that 65
Yeah,
degree.
and I think understanding what spare power you can build when you're building new buildings, because the last thing you want to do is try and alter an existing building and turn it into one of these things. So if you're building a school, why not build it and say, you know, I'm going to have the school as energy positive, if I can. You know, not all plots can. You know, we build schools in the centre of Cardiff. There's not enough land. But if you build them for up the valleys or in the countryside, there's plenty of land.
public
There's no
swimming
pockets.
pools, public swimming
Swimming
pools,
pools,
right? Yeah, 100 kilowatt rack of servers will very happily heat an Olympic-sized swimming pool. And most of those, particularly those local authority-owned swimming pools, they've got great amounts of power, and great amounts of telco, you know, so connectivity, and they've usually got some kind of comms room anyway. If that space was available to us to run AI training algorithms in, we'd very happily pay for it. And the waste heat can go heat swimming. Stuff like that is much more efficient reusing it.
Graham, you were going to put your hand up, and then Andrew.
Yeah, Nick,
And you are?
Graham Harrison of the National Composites Centre, and the National Composites Centre is going to host the Isambard AI supercomputer. Some of the thoughts at the moment, I don't know whether the timing is perfect or dreadful, because I understand that the computer needs to be commissioned in operation very, very quickly indeed. So maybe we've got to make the best use of technology available. But if this area is going to be perhaps a centre or a focal point for the UK national artificial intelligence initiatives, can we be thinking region-wide how to capitalise on that? Because it will attract other businesses in due course.
My suggestion about that, when I was asked, was that as that region, at one point there was an attempt to get planning consent for building houses on there. I think an estate of affordable houses with free heating would be a good plan for the area.
Absolutely.
And the only thing I would say from a regional standpoint, of course, don't forget computing is a very movable object. I mean, I've got clusters in the southern states of the United States, I've got clusters over in Asia, which are dialectic. So do be slightly aware that don't expect a huge rush of, it's not like in the old days round Soho where everyone wanted to be close to BT Tower because they were cheap fibre.
I think one of the only differences, and again, I don't profess to be an expert, but it's the research
Yeah.
computer. It's not going to be commercial.
Yeah.
So I think it will attract, and again, people.
And that's about ecosystem building, right?
Yeah. So that clustering thing, and I'll come to Mike on the innovation point in a moment. Andrew, introduce yourself.
Yeah, I'm Andrew. I work for Battle UK, so we're Battle taking on the development of the distributing in Bristol, and you said 90% potentially the energy used by a data centre is then comes out as heat.
It could be even higher. I
It
mean,
could be even higher. So
semiconductors are one of the most efficient ways of turning electricity into heat. I mean, people do make space heaters that are literally semiconductor panels
Yeah.
because it is such a phenomenally efficient transfer from electrons to infrared.
So one of my suggestions about 15 years ago was that a central heating boiler should basically be a computer.
Yeah.
So when the thermostat switches it on, it offers the message to the cloud. How about that?
Well, yeah, so, I mean, you were talking about a 2 megawatt data centre. I don't know how big that is spatially, but that's 1.8 megawatts potentially heat being generated, and that's enough for 1,500 homes.
Based on current computer
Sorry, hang on a
architectures- Go on.
minute. So that was 1,500 homes for 2
So there's a
megawatts.
3 megawatt all source heat pump we've got on the edge of Castle Park, and that produces heat.
Yeah, so just for reference, that 2 megawatts I gave on that table, that's basically 10% of today's #1 supercomputer,
That'll be about this room now.
which is in Tennessee, in
So-
so that's 29 megawatts actually.
So Isambard AI, what's the power?
Probably going to be a lot
Yeah.
And one of the considerations
I don't,
was,
unfortunately.
did the area have enough power?
Yeah. I think I did see a figure somewhere,
I think it's north of
2
2 megawatt.
megawatt. So
That's the case, that's it.
so that could heat.
So, yeah, and to put that in perspective, 2 megawatts is a large gas turbine combined cycle power station. I mean, it is a phenomenal amount of electricity we dump into computers, and we're turning it virtually all of it into heat. We should absolutely do something useful with it. We either need to recover it back to electricity.
And by the way,
or use that heat.
we actually pay good money, almost the same, sometimes the same amount of money, to actually cool that, to take that heat away.
So we have as a West of England thing, we've got a massive opportunity, albeit the timing is terrible as you suggest.
To be honest, actually, that when I met with Nick and we first started discussing this was back in April, wasn't it? Is I literally walked down the street and I saw this advert for Bristol Heat Network and I thought, oh my god!
Yeah.
So I brought that up, and
Yeah,
that was
yeah.
where the idea for this came from.
You know, we're looking for sources of heat in the city centre because there's not a lot of space, and wherever we can get waste heat, we use it.
So we should be.
So one of these modules that I just was talking about, just one, is about 1.5 kilowatts if it was fully loaded, right? So you know, when you think about that, when you boil your kettle, was it 3 kilowatts is the maximum you can pull out of a socket. So yeah, you don't need much. You know, if you start to distribute that compute everywhere where you need it, and therefore it's closer to where it's needed as well, which then you just design that into the house. Immersion heaters. Why not design an immersion heater?
Just go to BT and grab all the heat out of the telephone exchanges.
Yeah.
Is that concrete?
I think that is very.
I think we have
the-
near term and
We do.
long term.
Yeah.
I think the fact that you have the Bristol Heat Network is just.
So I would
opportunity.
suggest that kind of to stimulate activity and prowess, if you like, and make this part of the world the capital, you need to do some near-term stuff because that then triggers stuff. What you need to do is then make sure you've got the bits around it. So the innovation piece, we talked a little bit about.
Supply and demand.
Yeah,
That's something that
well,
West
there's
England combined centric
yeah.
absolutely do.
There's a supply and demand, but also how do you get the innovation happening in the built environment, in the computer architecture, in the application? You know, my world, Katie's gone. She did sneak out.
Yeah.
Okay. So we can't talk about my world. But from the innovation piece, Mike, you kind of host a bundle of entrepreneurs.
Yeah.
What do you think the kind of what could you do, for example, to stimulate innovation in this space?
So yeah, what Katie mentioned. I mean, as you've been talking, I'm thinking about actually the framing of the challenge to make really clear actually where the opportunities, because this conversation is really interesting, but we have meandered across huge numbers of applications and things we could do. I was actually really struck by what you said earlier, David, about the 30 times difference in efficiency between different ways. I mean, we're way out of my area of expertise now, but if we're talking about a 30 times difference in power consumption based on how something is programmed, that seems like a really, really obvious target for innovation. And so should we be framing challenges around whatever is driving that, make it really clear? And I think if you have some grand challenges that maybe we lay out as a region, then that is something that students can go at, that entrepreneurs can go at, that bigger companies can go at.
Yes, it's an interesting one because there are, even in this region, of course, there are people doing well with high performance computing, but also the sort of things that occur in gaming and graphics and all the rest of it, which also is quite demanding if it's done well, but both on the communication side and on the processing side. So that's an interesting topic. I mean, the thing that's intriguing me that I'm sure I'm going to spend some more time on is trying to work out what on earth is going on inside these machines. I can see where some of the problems are arising because of the massive over-optimization that's gone into these things. It's a sort of strange thing of a vanity project for the engineer and a sales opportunity when you put the largest possible megaflops on the sheet.
It's sales by checkbox.
when you actually take it apart and say, how would I really build this thing and design it if I wasn't following that historic trajectory, then you might end up with a very different answer.
Or just look at the new Apple chip. I mean, that's a prime example where they really have got.
Well, Apple is an interesting case in point because it has one of the best design teams in the world.
Yeah.
They only use the ARM license. They don't use the architecture license. They build all their own stuff themselves. So
And it's their own software
they're doing some
ecosystem.
pretty cool stuff.
Yeah.
Yes. So you know you can do a lot better than what's turning up in some of these mega servers.
Yeah, so I think, I mean, to your point, we are covering a lot of bases, and it's like what you can pick one area like we did the 30 times. There is tremendous. I mean, the human brain is 20 watts, and we take 2 megawatts to do it. Like, so there's a lot of opportunity for innovation there, right? And we already are doing it. We are doing some fantastic things that do major improvements. But one of the key problems in terms of what I've been doing in OCP is in reality, in my own industry, I'm trying to work across the silos. And our industry is so siloed from like the thermal designers, the power designers, the compute designers, we never talk to each other. We always assume these are my walls, these are my boundaries. And I think but taking this up to the regional level, it seems to make perfect sense to me that we've got silos between Rob here and ourselves in the computing world when we could really bring those together. And in my entire experience of my entire career, innovation happens when I take an expert from that discipline and an expert from that discipline, and I get them talking to each other, and I listen to them, and you say, hang on a minute, if you did that you said you can do, and you did that, we would hit magic. Things would just be so much more efficient or whatever. And I think just so innovating across the silos is what I've called the lower hanging fruit of innovation. Because inventing a brand new silicon process that's 30 times more power is really, really hard. You know, it's what they call DARPA hard actually in terms of, and anyway, I think that working across the silos is quite a low hanging fruit. The trouble is, it's the political and business challenges that make it so difficult.
In terms of themes for innovation, just focus on the efficiency. Everything else will come from that.
Right.
Everyone can stack them bigger and press the pedal harder, but you've ultimately got to be efficient. If you can get the cost of the power down, the cost of the cooling down, if you can keep the cost of the hardware down, and when I say cost, I mean cost is ultimately, is a function of output versus supply rate. So you've got to, it's all about efficiency. We've totally lost that, I think, in the last 30 years. The machines used to be super efficient, and now anything like
So I need to wrap up in a second. David, I'm going to pick on you. You kind of here as sole representative of that significant cluster in North Bristol around aerospace, where there's a lot of high performance activity.
Yeah, there's they've already from GKN Aerospace, so I look after our GTC, so technology centre, so we've got the ecosystem around there. So interesting stuff. So we've got lots of vertical aerospace now going in. But I'm sitting here trying to your point around silos is fantastic. We've got a problem at the minute. So thermal, love to hear from the computing world as to what you're doing internally, because we're looking at cryogenics, we've got cryogenics lab, we're looking at trying to deal with these different things with the thermal capability, so there's an interesting sort of synergy there. Sort of thinking. I'm also thinking around the amount of data. It's almost as if like aerospace has almost shifted the problem into compute, which is a weird sort of, if we become carbon neutral or net zero, and then all of that data and all that requirement is going into like.
I'm just looking at aeronautic design. We've gone from running these massive wind tunnels into these massive CFD clusters.
Yeah.
We haven't really. It's not actually becoming any less power hungry. If anything, it's become more power hungry.
So is you and your peers in that community invest in R&D and develop new products and capability, taking on board some of this thinking, you could drive change, and if we tap into that, and then our colleagues from IBB and DBT can go and promote to the rest of the world that this is actually where it's happening, because GKN and Rolls-Royce and
thermal management.
Nick, I think there's another opportunity, just picking up what you were saying about data, and and just ripping off that, so within the part of the combined authority I sit alongside Alex, who's our new head of place strategy, so he's doing something similar to what I've been doing for digital for place. And just thinking about the data, there's probably a fairly easy exercise to map all the places and people who are generating heat, like yourselves, and where they are across the region. Look at that then and overlay in terms of what spatial development plans we've got, so where we're thinking about building houses and stuff. Who can move the heat around? So I'm thinking about that and fall in the heat network and look at what the opportunities are.
And of course the Germans have been doing this for decades. They reuse a huge amount of waste heat.
Called networks, isn't it? Which is roads, digital.
Refuse disposal is a big one because they burn their waste and turn it into heat and then distribute it out to the houses.
Processing.
Yeah.
One thing, you need to be slightly careful about this because there are two threads here. One of them is saying, how best can we use all this enormous amount of heat that's being generated out of computing?
And
The
how
other
do
thread
we
is saying, how do we
minimise
get rid of it?
Yeah.
So when you've converted all your houses into making use of all this heat, then it's not going to be there.
Okay, has anybody feel they haven't had the opportunity to ask a question? Yeah.
Just say one point. I think it's thanks to some kind of digital customer. The ICT sector is an enabler of net zero sustainability as well as a contributor to its own carbon footprint, right? The 3% figure was referenced earlier. So there's sort of two distinct sides there, and there's a lot of talk here about maybe the operations or the manufacture of compute systems, which I think is really, really important, right? You look at circular supply chains and so on and so forth. But ultimately, it's that other side, which is, really to drive the sort of net zero agenda sustainability. You've got to get widespread industry adoption. And the opportunity, therefore, maybe for this region and combined authorities, how do you bridge those two things together, right? It might be, through those innovation-based challenge calls where you've got big industry players like Airbus or GKN, whoever it is, saying we've got these particular challenges, and the combined authority convene that into challenge calls or accelerators or something like that.
I'm seeing that the start of the plan here. Are we
taking notes?
I am. Are we feeling more optimistic now or less optimistic? I'm feeling more optimistic. Yeah.
We've had the folks producing the heat and the guys who want to distribute it in one room. I mean, that's got to be a good start.
Yeah. So I'm going to wrap up now. I think I found it an interesting conversation. I hope everybody in the room has taken something away and or perhaps feel minded to come and offer support in some form and continue the conversation. I think it kind of does come down to the combined authority to be the holder of the conversation for the time being. So,
make a very quick point?
Please, David.
Does the combined authority talk to South Wales? Because the expertise in semiconductor manufacturing that's nearest to here, for historic reasons that you understand fully, is in Newport and Cardiff. and they're good. I mean, they do compound semiconductors. And incidentally, we do have a number of relevant expertise that's emerged here as well in that area. I mean, silicon photonics, for example, is a very promising technology in some forms of communication and high-performance computing applications. And we know a lot about that.
So the question was asked over lunch about collaboration between Bristol, Bath and Wales, and the answer, well, what did you take away as the answer?
There's definitely collaboration going on, and if anybody wants to connect with something that
So I think it is happening. There's always more to do, but so I'm going to kind of bring us to a close. Sorry, you had a question.
Yeah, I have some contacts in the compound semiconductor applications catapult.
And you are, sorry?
Helen Duncan, I've got two hats on.
Okay.
I work with a non-Neumann computing architecture company startup called British Memory, but I'm also on as a consultant. I have worked with the catapult.
Okay.
I've got a background in compound semiconductors. They have the compound semiconductor applications catapult is very involved in energy efficient networks.
Yes.
And there's a sort of a circular thing here because the mobile networks are running on data centers. So what we're using to move the data around is actually using data as well. Yes. And
So-
6G is going to be much worse than 5G as well.
Yeah. Okay, thanks,
So,
Helen.
yeah, I'd be happy to liaise.
Brilliant. Okay, so there's goodwill in the room as well, and in the spirit of this region, I think there's been sharing and learning, and the start of an exciting new collaboration. Well, building on existing collaboration. So thank you all for joining us. Thank you, panel, very much. If you'd like to join me in thanking the panel.